Good afternoon, my name is V. Pradeep Reddy and my roll number is 2095182151 and I am from Aeronautical Engineering A section, 7th semester. And subject aerospace structural dynamics and topic is control of lateral motion in moving webs. Abstract. A partial differential equation for the lateral motion of a web convenience system is derived by modeling the web as a viscoelastic beam under axial tension. This model treats the web position between rollers as a function of both time and space, assumes that there is no slip between the web material and the rollers, and incorporates the web material's viscoelastic damping property. A finite difference approximation of the model is used to simulate a typical two-span web system. The finite difference approximation is validated by comparing its frequency responses with those of an analytical frequency domain model. The analytical frequency domain model is used to design feedback compensation strategies that make the two-span web system less sensitive to upstream disturbances. The results show that using a transverse vibration model incorporating viscoelasticity to design even simple classical controllers, it is possible to make the web system less sensitive to upstream disturbances at the sensor location. Introduction. Webs are flexible materials that are very long in comparison to their widths or very wide in comparison to their thicknesses. Many objects made of rubber, plastic, paper or steel are in web form at some stage of their production. A web conveyance system with tension causing the web material to travel longitudinally past a series of rollers is considered as the web material travels longitudinally between rollers. The material also tends to have lateral motion for a given system. There exists an optimal path along which the web edge must travel to achieve maximum efficiency. Disturbance inputs to the web conveyance system may cause the web edge to deviate from its optimal path, leading to inefficiency and inferior product quality. For industrial web applications, tight web edge control is important at several locations in the process. Modeling the lateral motion of a moving web. The equation governing the deflection of a flexible beam is derived as EI dou power 4y by dou x power 4 plus m dou square y by dou t square equals to 0. The beam equation for a viscoelastic and solid under axial tension and no slip between the web material and the rollers is then EI dou power 4y by dou x power 4 minus t dou square y by dou x square plus ni dou power 5y by dou x power 4 dou t plus m d square y by dt square equals to 0. Boundary conditions. A typical single span web system is shown is the longitudinal velocity of the web, and the arrow indicates the direction that the web is traveling longitudinally. Each web span is composed of two rollers, an upstream roller at the beginning of the span and a downstream roller at the end of the span. On each roller there are two contact points that serve as boundary conditions, an upstream contact point and a downstream contact point. Single web span diagram. At different steering angles. Upstream boundary conditions, steering angle is equal to 0. Upstream boundary conditions, non-zero steering angle which is not 0. Two-span web systems. Two-span web system configuration. Physical properties of the web material being considered. Property Young's modulus value equals to 1.75 into 10 power 7 pascals. In viscosity, (2.57 into 10 power square 10 square). pascals, axial tension 46 newtons, width 0.36 meters, thickness 0.001 meters, density 1000 kg per meter cube, lateral motion moment of inertia 3.88 into 10 power minus 6 meter per 4, length of span 1 2 meters, length of span 2 1 meter. Conclusion: this presents a model for lateral dynamics of the webs that are made of viscoelastic materials. The frequency domain analysis used for controller design purposes is also unique to this research.